Today we are going to do section 5.2. I'm missing the point here. Let's fix the point. Okay, and then we will next do scanning books. Okay, first we'll repeat the page we already scanned last time, but I'll show it to you again briefly. And specifically, let's see, this part, that's, well, that doesn't really say much. This part, the new part, okay, that should be good enough. Next page, 156 and 157. Let's see, let me hold it steady like this. Okay, that should do it. And then a little closer on top. Okay, and then a little closer on the bottom. That's good enough. Okay, next, page 158 and 59. Here we go. That is the whole page. Oops. That should be good now. And what am I doing? Okay, yeah, zoom in on top a little bit, closer on top, like this. Keep it parallel, well, and on bottom. Okay, that should do it. So let's start on page 155. And first, let's consider certain basic properties of the Stieltjes integral. A lot of them are similar or identical to the Riemann integral. Okay, so let's look at this thing. First, there's a list of 9 properties, and we'll look at them one at a time. But before that, we will go back to the original definition of what is the Riemann integral. Okay, the Riemann integral is this particular sum, a limit of the subdivision, the maximum distance go to 0 of this particular sum. Okay, and yeah. And then where the subdivision goes from A to B. Okay, so refer to this constantly as we go through each property. Now, so having done that, let's look at property 1. Property 1 says if f of x equal to 1, then it equals alpha b minus alpha a. The reason is because when you look at this limit, this summation, f is just 1, so each one is subtracted by the other one, so there's a telescopic situation happening here, which everything in the middle got canceled out except the last term and the first term, which is where 1 works. Next, let's look at property 2. If alpha x is added to some constant, you plug it into this limit, then you quickly notice that for each alpha xk, okay, will be subtracted by the next one, both added to the same constant. So then it's just this thing. The constant gets subtracted out, which is why you can remove the constant in the d alpha x. So next, property 3, when you have a constant on the inside, okay, you can pull it out because of the summation. If there's a constant in here, you can just yank it out of the summation. So that's property 3. Next, let's look at property 4, where you have 2 functions together. What happens, well, if you have 2 functions together, so you have f1 and f2 of psi, of the same psi, multiplied by the difference of x's, okay, and the summation is just, you can break it into 2 summation symbols, right? So that's why they equal to the two integrals just individually. Okay, okay. And next, property 5, still referring to this thing. Okay, let's see. Is my screen getting dark? Doesn't matter. And let's continue this thing. We have property 6. We have, let's see. Still referring to that limit, okay? Property 6, we have now alpha is different. Now, if you write it out, then it's just you have 2 alphas subtracting by and then that just breaks up into two f's, right? One with alpha 1 and one integral with alpha 2. So that is why that works. Again, because summation, you can break up summation symbols when it comes to addition or subtraction. All right, and it seems like my camera is getting dark, so I'll let it maybe move back a little bit. Okay, and next, what were we doing? Summation, add or something? Okay, now I think we just did this one. The sixth one, we're going to the point C in the middle. Okay, so that is that you use when you do the summation, then the endpoint has to be C. You see, you break the summation into two summations, one going from A to C, right? And the next one going from C to B. But being that, as the book says, that down here, okay, the explanation is down here. Being that the subdivision delta must be chosen to include the point C. Now this is okay because in theorem 1 that the definition of limit exists independently of choice delta. So we'll just choose delta as with C in it. That's all, the two deltas, and that would not change anything. Okay, so that is that. So think about that. If that doesn't seem to make sense to you, just think about it for a few seconds, okay? And then repeat that sentence in your head. And so next we'll consider property 8. No, what were we doing before? 7, right? Okay, so 8. 8 is the absolute value theorem, and that applies for the same reason that it applies to Riemann sum. That is, you apply this formula right here, okay, and the inequalities, and then apply the previous formula. What is that? 7? Why does it apply to 7? Give me a second here. I see. I forgot to mention 7. Okay, 7 says if one function is less than the next function, then the integrals are also less. Well, that's because alpha, when you look at the summation, this term, alpha is an increasing function or non-decreasing. So as a result, this term is always positive. So if one f is less than or equal to the next f, then the integral, therefore, is naturally also less, see, because it's being multiplied by a positive number anyway. So that's why the summation works. Okay, so that's why I said it applies to 7. So you use this inequality, okay, and apply the fact that if one is less than the other, then this the corresponding function integral also is less. Apply this thing, that will show up this right away. Yeah, and anyway, so and finally, property 9. All right, we have this absolute value. To prove that this is less than or equal to the maximum f times the difference of the ends, we apply a whole bunch of them. That is first is less than the magnitude of f on the inside. That's from the previous theorem, and which is less than equal to maximum f. That is from property 7, right? And then which is which this is equal to this. The integral is, being that this is a constant, okay, you can just take it out. That's from property 3, taking the constant out. And then eventually this is equal to that, and that's by property 1. And so that establishes property 9. Okay, so the rest of this page explains somewhat of what I just said about the first 9 properties. Please read this, go over this yourself. Okay, and it also continues to the next page. And specifically, notice that it says that this theory, all the properties work in case alpha x is a decreasing or non-decreasing function. If it points down, that's fine too. That all the logic applies the same way. Yeah. Anyway, so that's that. Yeah, I specifically mentioned right here that if alpha is a decreasing or non-increasing function, just flip all the inequality signs to the other way, because then you're at the negative sign, you know, when you're dealing with negative signs, then you just inequalities flip when you do negative signs, and that should be, so yeah, that should be right. Next, let's look at page 156. Sums. Sums of what? Step functions. Now remember step functions? I have always disliked step functions because I always get mixed up with at this jump which one is the solid dot and which one is the circle and all that stuff. So please pay careful attention to that. And anyway, so we have a step function. Let's say we have a step function which jumps at point ck, okay, where ck is the subdivision between a and b, but c doesn't equal to a or b, okay, so it's all in the middle, and then it jumps at the point of ck of amount hk, all right, so then alpha is, and then so as being as a step function, alpha is constant in between, okay? So that means d alpha is 0, right? Because d alpha is subtracting from the definition, is subtracting 1 point from the next. And if the difference is 0, then your sum is going to be, your multiplication, that part of it is going to be 0. So as a result, then, and the difference, step function means this is going up, by the way, okay? We're not stepping down right now. Let's consider the step function that's non-decreasing. So then your steps are going up, and then and they're different by a certain amount. Where all right. So then, as a result, the integral then, if you think about it, then it has to be equal to h. The integral being that any level point, okay, the integral is going to be 0, right? I mean, yeah, the multiplication is going to be the alpha k, the formula where alpha xk. I should show you the formula. Where's my formula? Yeah, right here. This formula here. On page 151, where alpha xk minus xk minus 1, if xk and xk if the alpha are the same value in those two places, being this is level, then the difference here is going to be 0 anytime it's level. If these two values are the same, so then the only summation value you're going to get out of this is actually this thing, right? That is only at the jumps. You just collect all the jumps, then you're good to go, basically, is what that means. And all right, so so that's one mention of step functions, which I believe we're going to do quite a few step functions in the homework, which, yeah. So you just have, when it comes to step functions, they're constants except for the jumps. So you just have to pay careful attention to all the jumps, and don't forget any of the jumps, then you're okay. So next, let's look at section 2.3, the Riemann integrals. Now, let's say our function f is in C, continuous, and alpha is in C1, is differentiable. Okay, that's important in the closed interval a to b. And then the integral of f of x d alpha x is the same as the same integral f of x of alpha prime x dx, which is, you would guess from just looking at the differential, okay? But that is actually true. Now, this is going to help us do a lot of the homework, especially when if alpha is differentiable, right? You can just turn it into a regular Riemann integral by taking the derivative. Now, to prove this theorem, or to prove this thing, this is not even a theorem, whatever. But in equation 2, to prove the equation 2, we're going to go back to a good old law of the means, right? And the MVT, mean value theorem, on page 9, the first one we ever learned, which states that, okay, let's look at this. Being that there's going back to the formula, the sum is equal to that times that, which is, you can stick the derivative here, right? And then go back to xk, and xk minus 1 is self. Do I have it written down here? Yeah. Let's show me what I wrote. That is, yeah, this is the original sum, right? And this part can then become this, alpha prime eta k, and times the difference of the x's. That's by the mean value theorem. And so when you sum this all the way up, I'm missing a summation sign here, but anyway, if you sum this up, then that is the same as the integral, see? Because then, oh, actually, that's not all, okay? We also need to quote the Duhamel's theorem. Let me fix the summation sign. All right, I fixed the summation sign, so we have a summation sign here. And this thing, what is that? That's the same as the integral with f and alpha prime by the Duhamel's theorem on page 173, which I'll flip it there right now to show it to you. Here's Duhamel's theorem, okay? And as you can see, this summation with the and all, see, that's f of psi k, g of eta k. So psi and eta are not necessarily the same thing, but that makes no difference. See, once you squeeze it all in, right? I mean, everything's getting close to each other, and it end up being correct. That is, the summation does become f of x and g of x. In our case, g of x is alpha prime. Okay, yeah. So that is applying Duhamel's theorem. Then this will become what we need it to become, which is that formula that the integral of, oh, this thing right here. So we're driving at this. That's the integral of f d alpha is the same as integral of f alpha prime dx, which can be very convenient, of course. If alpha prime is easy to do, then we can just turn it back into our familiar Riemann integral. So next, let's look at section 2.4, where it says that we have assumed that f is in C and the function alpha x is non-decreasing, right, pointing up. Now, with these conditions, all the integrals exist by theorem 1. Well, yeah, theorem 1 just says that with these conditions, that your integral exists, okay? And so the properties that we have looked at is the various properties pretty much can all be proven. Even without some of these properties can be proven without these conditions. Okay, that is the condition f equal to belong to C might not even be necessary, or I think all we require is that alpha x is increasing or decreasing, as how we proved the properties in the previous page. Now, okay, now let's focus on, well, assuming everything exists, of course. So next, let's focus on this sentence. It says, a property like property 5, and let's look at property 5. What about property? What is property 5? Okay, now property 5 says that, for example, if you have the sum of something, okay, then you can break it up into two integrals. So basically, one integral can be broken into two integrals. So if that's such a property, okay, it will hold if you can prove two of the integrals exist. Because if two of them exist and the equation holds, then the third one had better exist, right? Because the equation holds. So it doesn't make sense that the third one doesn't exist when it also equal to the other two. So then, so as a result, that yeah, see, the reason is because the third exists by virtue of the theorem concerning the limit of a sum of two variables. So when you apply the limit, then two of them exist means the third one exists. Anyway, so let's look at the next page. Therefore, if f is continuous, okay, and alpha is alpha 1 plus alpha 2, so alpha is breaking down into two chunks, right? And alpha 1 is increasing while alpha 2 is decreasing. Remember, the properties apply for decreasing functions as alpha pointing down as well, right? So then if these things, if f is C and alpha x is alpha 1 and alpha 2, each one is increasing and decreasing, then the integral exists, and then the integral equals to the alpha 1 plus alpha 2. The reason is because this one exists, right? Because alpha 1 is strictly increasing, f is continuous, so that exists. This one exists because alpha 2 is decreasing, and the alpha not decreasing is strictly called non-increasing, okay? But sometimes I might just call it decreasing. I mean, the arrow is pointing down, you know, let's not be too picky. But anyway, when I say decreasing, I mean non-increasing. So anyway, so then, so because these two integrals exist, that one also exists because they're equal, you know, all the time. So it has to exist. So, okay, as a result of that, then let's get to definition 4, okay, which gives us a definition called bounded variation. A function alpha x is a bounded variation in an interval x between a and b if alpha x is alpha 1x plus alpha 2x, where alpha 1 is increasing or non-decreasing and alpha 2 is decreasing or non-increasing, okay, pointing down in the entire interval. So if your alpha can be broken into those two chunks, if it's possible, okay, then we can do this. And is alpha possible? Well, most of the time, yeah. There's a trick that we'll show in the homework to how to break down any old function really into an increasing and a decreasing function being added together. All right, so let's next look at example A. Okay, we have the good old sine x, right? And we are going to show that it is of bounded variation. Now, let's see. Let me think about this. Now, I shouldn't say that all functions are of bounded variation. I mean, sometimes it might go nuts, right? Especially if it goes to infinity. But generally speaking, a lot of functions, basically a lot of functions that we can make it break it into alpha 1 and alpha 2. So, well, we'll see to that, okay? And so let's look at example A anyway. Here's the function sine of x, and we're going to prove that it is of bounded variation, which means we can come up with some kind of alpha 1 and alpha 2. Alpha 1 going is increasing, alpha 2 is decreasing, and added together such that sine equal to alpha 1 plus alpha 2. Yeah. And to do that, we have, so the book came up with this solution. Please confirm that these two equations add up to be sine x at each point. The equations are defined in two parts, okay? And they add up to be sine x everywhere, in the range that we need, which is 0 to pi. And one of them strictly is, not strictly, one of them is increasing, the other one's decreasing. And therefore, sine of x is of bounded variation. But that's not all, okay? And there's more than one way to skin the cat. For example, you can also define alpha 1 to be 2, and alpha 2 be the sine x minus 2. And that can also, that will also satisfy this condition. The sine x is equal to alpha 1 and plus alpha 2, and then alpha 1 alpha 1 is non-decreasing. In this case, it's not increasing anymore, but it's non-decreasing, and alpha 2 is whatever it is, non-increasing. So, yeah, well, anyway, I plotted something here, but I don't think you need to look at it. For example A, it's, yeah, you can just work it out yourself. So as a result, the point is there's more than one way to skin the cat, right, of creating the bounded variation things. That is how to create alpha 1 and alpha 2. There's more than one way. So that is, now let me see the next comment. So far we have done the integral, okay, of f of d alpha as we only so far have defined it for alpha going up, non-decreasing, okay, or alpha going down. But with the bounded variation equation here, now we know that we can now calculate this integral as long as alpha can be broken down into two of these things, you know, one non-decreasing and one non-increasing. And so our Stieltjes integral can now be defined in more than one way. So the integral exists. On the left exists, yeah, and its values given by adding these two integrals together. So these are the ones we have learned, and now we have a third option, that is by combining the two, which greatly increase our definitions of the Stieltjes integral. So let's look at what is that? Example B. Okay, let me look at this. Okay, for example, B, well, we have alpha, some weird function that equals to 1, except that at 1, it equals to 0. Okay, and then alpha 1 we define as this, and alpha 2 define as that. Now, please confirm that alpha equals to alpha 1 alpha plus alpha 2. Alpha 1 is increasing, non-decreasing. Alpha 2 is decreasing. And then all these things work out. Okay, if you stare at it for a few moments right now, then you will see this is the case, and verify all these numbers. So with that we have come to the end of this section. For homework, please do on this page 150 something. What is this? 157. All right. Homework on page 157. Please do problems. Let's see, 6, 7, 8, 10, 11, 12, 13, 15, 16, 17, 18. All right, and when you're done, I want to talk about them. So the homework on page 158, we are just doing a bunch of problems with the Riemann by converting into the Riemann integral. Okay, like it says section 2.3. Where is it? Right here. So we're just converting alpha x into alpha prime, d alpha x into alpha prime x dx, and then cranking out the integral the old-fashioned way. So that should be easy enough. Right? Let's say problem 6. D sine x becomes cosine x dx. Then I just plug that into the calculator. There is a quick way to do this from calculus 2, but I don't want to bother with that. So I typed it in and out pops the answer. Next, problem 7, the same thing. Okay, and d sine x becomes cosine x dx. And then I popped it in. Actually, I didn't even pop this in. This is the integral of cosine squared is, I believe it is pi over 2 because of this. This is a trick that's taught in, I don't know, calculus 1 or something. I just want to mention it real quick. It's a cute little trick. It doesn't do much, but it's still worth mentioning. 0 to pi, if you have to do cosine squared x, okay, dx. What is that? That is that's the same as 1/2 of, you do cosine squared x plus sine squared x, and then doing this integral, okay, 0 to pi, and then divide by 1/2. And let me not spend too much time on this. This is nonsense. Anyway, if you do the integration somewhere, okay, use the calculator, it should come up to be pi over 2. Anyway, the point is, yeah, it equals to pi over 2 if you type it into the calculator. So next, let's look at problem 8. Problem 8 is the e has an absolute value there. That changes nothing. You just, the calculator can even do the absolute value, at least some of them can. The Wolfram calculator can. But either way, if you don't do that, then you can just calculate from minus pi to 0, okay, with e to the power minus x. And then d cosine x is, of course, minus sine x dx, and then do the integration. And so I did the way of simply putting it as a negative sign. And in e to the x, but you can also type in absolute value up here, which spells ABS parentheses. Okay, so either way, you'll come up with something, and they end up being the as things of opposite signs. So then when you add them up, they equal to 0. And anyway, so that is that's problem 8. So next. So problem 8 equals 0, and that does check out at the back with the back of the calculator. And then next, let's consider problem 10, which is, let me look at it first. Problem 10 says alpha is 2 all the way through, okay, except in the interval from minus 2 to 2, where alpha x equal to x. So you have a break there and have a jump, right? And pay special attention to the jump. So to do that, we're calculating the integral from minus 4 to 9, right? Okay, so to do that, we have to calculate from -4 to 9, all we care about is the integral equal to 0 until you get to the point -2 where there's a jump. And by the definition of the integral, the jump is going to be equal to f at that value, and that is x cubed at -2 times the jump, d alpha x. The jump is negative here, so times -4 plus, and then you continue adding, okay? Then the next part where alpha x is just equal to x, so from -2 to 2, you just integrate from x cubed, and that's about it. The rest of it is all level again. So, and there's no jump here, so you don't have to think too hard. So then, so this is the only concern. I mean, the only catch here is right here. Now, this is of course 0 because x cubed is an odd function, and you're integrating it from symmetrical points. So that value is 0, which means the total value of the integral is just calculated at the jump, which is equal to 32. So that's problem 10. Next, let's look at problem 11, where we have some function. We have to come up with an alpha such that whatever it wants happens. Okay, and f is continuous, so we don't have to think too hard there. But alpha is going to be need to have a bunch of jumps. So here is what is problem 11, right? So here's what happens. What happens is that we'll define alpha 1 and alpha 2 and then add them up to be the result. Now alpha 1, we'll do all the increasing part, okay? That is all the positive values like f0, 2f5, and 4f10, like this. f0 is right here. I mean, that's not f0, that's what alpha is. Alpha need to be 0, okay, at 0, and then the step function defines, and then it goes up 1, okay, because there's a 1 times f0, and then it goes level because until it gets to 2. Because we are only focusing on when it increases. And being that it's non-decreasing, when it's not increasing, we'll just have it go level. So it goes level until it gets to 5, F5, where it jumps by 2. So we'll do that, okay? We'll make alpha jump up by 2 units. So 2 times F5, and so on. And then these two, so the alpha F5 need to be defined as is still defined as 1. And when you do this, keep your mind on this equation, how you might make it happen. See, the multiplication when alpha is subtracting and going to 0 and stuff, right? The difference is going to 0. So bear that in mind as you design this thing. So continuing, I keep going up, okay, at the next jump. So these are empty circles on both ends because I need this eventually is F10. I need F10 to be up here. Okay, so the alpha has to be solid here, and so that your jump makes sense. So then eventually it becomes 4f10. That's that will achieve the first part. The second part is similar. That at 1. When it's 1, that is going down. So we consider all the subtracting of things, which are 2 of them, minus f1 and minus 3.7 f3.7. So at 1, it will the alpha need to be equal to whatever that is on top. That's 0. Okay, this is 0. It's going down from 0. So alpha need to be 0, and then it drops down by 1 here. So it goes down to minus 1, and then drop down by 3.7 more. So it goes down to negative 4.7, and so on. So please look at this very carefully. And you see the purpose is so that all the jumps come out to look like this. So you break it into 2 jumps, the positive ones here and the negative ones on the other side. And when you add it up, that will become f. And yeah, and that should be the end of problem 11. So next, let's look at problem 12. Let's see. Okay, problem 12, we're redoing example A, all right? So we have these integrals, and we're just gonna, plug it all in like it says, and then we'll see what it equals. So that's just a matter of following instructions, right? We'll have alpha 1, alpha 2 doing the integration, it equals to, well, whatever it equals to once you get, and following property 6 and so on. So eventually we get it equal to -2. Or we can go do it direct. Instead of having alpha 1, alpha 2, we follow directly property 6 by breaking down this integration into 2 integrals such that, where is it? Well, whatever. I don't even know for sure what I'm doing here. But the point is well, there are 2 ways of doing things, but they come up to, actually the 2 ways aren't even that different, I don't think. Anyway, so the point is the answer is 2 if you follow the instructions of doing problem 12. Okay, next let's consider problem 13, which I'm just going to show you what I did. Okay, some kind of a simple step function here, I think. And please try to make sense of this yourself. And then, so let's move on to problem 15, which says that we have to, well, I have to find my book first. Let's see. Okay, problem 15 says show that sine 3x is bounded. That is, we need to find the alpha 1 and alpha 2 for sine 3x, which is instead of x, it's just x, as in the example. So to do that, we have we follow the same principle as we learned from problem 11. That is, when the function is going up, then we'll put it into alpha 1. And when the function is going down, then we'll put it into alpha 2 and then add those two together. They both start at 0, I think. Yeah. So then when they add together, it will construct our create our alpha 1 and alpha 2 for us by following that principle. So I'll show you a little bit of what I did here, but a better indication would be what I graphed on the Desmos calculator. Okay, here is, let me move this over a little bigger. All right, so that is what I have. On the decimal calculator, you notice this is the alpha 1, okay? And I even wrote it over on the other side. See, it says alpha 1 on the other side. And the second one is alpha 2. What you do, if you define it this way, is each part, when you add it together, see, this is sine 3x, that's 0, so add it to be sine 3x. Similar here, that's 1, and that's minus 1, it add up to be sine 3x, etc. See, each one of these add up to be sine 3x. And then as what I do is the graph is increasing or level. See, it stands 3x, then it stays at 1, and then 3x plus 2, and then it stays at 3. Now to see the graph of this, okay, let me make it a little smaller. Okay, here's what Desmos graphed for me. Now what I'm showing you right now is also how to graph a sectional function on Desmos. See, you have, as you can see, the green one, this one is the alpha 1. As you can see, it goes up, goes level, then I have it connected or patched up so that each level line, it connects to the previous highest point. See, it goes up, go level, go up, go level, right? And similarly, alpha 2, when alpha 1 goes up, alpha 2 goes level. And when alpha 1 goes level, alpha 2 goes down, and so on. So you just keep doing that, and until you get to the end, is as you can see, alpha 1 is non-decreasing, alpha 2 is non-increasing, and when you add them up point by point, they will equal to sine 3x, which is the red graph in the middle. So it works out very nicely. To emphasize on, I want to show you how to graph these kind of, what do you call these things? Sectional? No? Well, anyway, these kind of partly defined functions on Desmos. What you do is you use colons. See, the first section, x going from 0 to pi over 6, dot colon, okay, is plotted as sine 3x, comma. Next section, pi over 6 to pi over 2, colon, and that equals to 1. The whole section just equal to 1, and so on. See, until you get to the end. Use the bracelet, and then everything. The equal to alpha 1, I added that later. Okay, yeah, that's not in the graph, and so is this. I just added that later. But the graph itself is plotted exactly like this. And so Please feel free to graph this in the Desmos calculator. Oh, you don't have to graph this. It's just that I think it's cute that the Desmos calculator is able to graph these sectional things as well. One part that define more than one part of the function, and it's nice to look at. You see, I mean, how beautiful is this, right? This looks totally awesome. Everything's smooth and perfect. So that's that. And this is following, I got this idea from doing problem 11, you know, where you gather all the positives and keep going. And as you can see, this same trick can be used for basically most functions, right? I mean, functions going, you know, whichever way it goes. You just round up all the increasing parts to be alpha 1, and then round up all the decreasing parts to be alpha 2. And when alpha 1 isn't increasing, you keep it level. And when alpha 2 is not decreasing, you keep it level. And then the whole thing will add up. And that is going to be true in the next problem as well, problem 16, which, what does it say? Problem 16 says, same problem for sine 3x. Okay, so I didn't even write that down. So the difference between sine absolute value 3x or just sine 3x is just, you know, it has a bunch of bumps. Where sine 3x go like this, sine absolute value 3x will have 3 bumps in the same range. So let me show you what that problem looks like. Let me load this thing here. Here we go. First, so the principle is exactly the same as what I showed you before, right? You have a bunch, the whole thing is sectionally defined, except now there are more sections because this thing goes up, down, up, down, up, down. What is that? 6 times, right? There are 6 different ways that it turns. So that's what we do, okay? We define each section properly. And as you can see, the alpha 1, that's the blue line, okay? It goes up with the same graph and then goes level if the sine 3x is not going up. And you just keep crawling up like that. Similarly, the alpha 2, which is what is that, green? The green line down here, it goes level when the graph is going up, and then it goes down with the graph when the graph is going down. And so that is how I type this whole thing in. As you can see, let me show you the whole thing. Okay, as you can see, I typed the entire thing is typed into the Desmos calculator. It's able that's 6 different conditions. See, that's alpha 1, right? That's alpha 2, and all 6 conditions got typed in, and the calculator is able to handle it. See, no problem. And then well, anyway, this is a magnified version, so you can see it better in case this is too small. So this is just repeated. I put the part of it on the second line so that I can fit. What is that? Yeah, I used the absolute value for this. Yeah, because this sign has the absolute value in it. So as you can see, the absolute value is in here. And again, these two add up to be sine 3x at any different point. And just add vertically. That is, for example, the first one, sine 3x plus 0. Next one, 1 plus sine 3x minus 1. Okay, they always equal the sine 3x. And you just have all 6 things accounted for, and then you get yourself a nice, cool graph. And it's not very complicated, okay? You can totally do this yourself, right? And it's pretty easy to do, but unless you're an artist, you probably won't be able to make it look as good as this. Right? I'm not good at drawing, so I'm very proud that I'm able to come up with this stuff with the Desmos calculator's help. So that is a fantastic calculator, right? To be able to graph this thing. and right, so that's about it for problem 16. 16? Is this 16? Let me check. Next, let's look at problem 17. If alpha is of bounded variation, and we get a subdivision of xk, right? And we need to show that there exists some kind of a constant such that the sum from I to n, no matter how big n is, of that difference is going to be less than m. This is, and in fact, we can even use this thing as the definition of the bounded variation. That is this thing. There exists some constant so that this sum is going to be less than m no matter how big n gets. That is how much you divide it. So that is where the bounded comes from, right? Bounded variation. So let's demonstrate problem 17. To do that, we have, I have it written down here. We have, if alpha is alpha 1 plus alpha 2, alpha 1 is non-decreasing, alpha 2 non-increasing, and from the principles of problem 11, 15, and 16, well, that's what we're basing this on, maybe. Actually, why did I say that? Well, it doesn't matter. Let's keep going. So the sum of alpha xi minus alpha xy minus 1 can be written broken into two parts, right? Because being the alpha is alpha 1 plus alpha 2, so we can break it into alpha 1, okay? And then plus alpha 2's, alpha 1's difference plus alpha 2's difference. All right. So then as a result, this is that thing is less than or equal to splitting the sums individually. I mean, each item can be split this way, so the summation can be split as well. And then this by the triangular inequality. Okay, and what is that? That is the same as being, remember, alpha 1 is non-decreasing, right? So that, if you add it all up, that's basically alpha b minus alpha a. If, yeah, and the other one is, because you calculate them at the absolute value, but this is all positive, whereas that is all negative, so the max is a negative number. But either way, they are two fixed numbers, regardless of n, how many times you cut it. So then this two numbers add together becomes the maximum that we're looking for. So that should be that. And next, let's consider problem 18. Let me show you problem 17 again. Okay, that should be good enough. And then let's look at problem 18, where which is based on problem 17. All right, let's see. Problem 18 says, let's say we have an alpha. Okay, it is 0 as 0, and then it is 0 on some intervals that's approaching 0, and it equals to 1 on other intervals that's approaching 0. You can draw this thing out to look more carefully. So here's our alpha, okay? We consider only the from 0 to 1. From 1 to 1/2, alpha equals to 1. From 1/2 to 1/3, alpha equals to 0. From 1/3 to 1/4, alpha equals to 1, etc. So you just keep doing that, and it does that infinitely. All right, and you just keep going 1 and 0 and all that stuff. And so now what? Now what we're gonna do is we'll come up with a subdivision where x1 will be in here. Okay, x0 is 1. We'll call this x0. Yeah. Something like that. We'll flip the number the other direction. Doesn't matter which way we go with it. Okay, so x1 is somewhere between 1 and 1/2. Okay, x2 is between 1/2, 1/3, etc. So if we do this kind of subdivision, we stop at some point. Okay, and then so we eventually stop at xn, where this relationship holds. Okay, xk will be less than 1 over k, but bigger than 1 over k plus 1. So if we do that, then this thing right here, this summation from the previous problem, which in the previous problem we calculate this thing, right? And so we're going to calculate this summation. Now this summation will be equal to, if you stare at it long enough, after I find out which page I'm on. Okay, here we are. So this summation is going to be, being that each xk is bigger than the next one, right? So it's equal to, well, we have, let's see, this is alpha xk minus alpha k minus 1 is going to be, being the alpha is defined, okay, so then alpha xk minus alpha xk minus 1, being that each one is in a different part, right? The difference is always 1. These differences, so that when you add it all up, slapping on the absolute value, the total is going to be n, right? And which means that this equation right here, as n, this equation we have in the previous problem, as n goes to infinity, this sum equals to n, and as n goes to infinity, it's not going to be bounded. Okay, so this condition does not satisfy. And if it doesn't, being that in problem 17, it says if alpha is of a bounded variation, this condition is guaranteed to satisfy. And now we show that the alpha in problem 18, this special alpha here, x here, being that it does not satisfy the condition, therefore this alpha is not bounded in 0, 1. And okay, that should be the end of this section. I should show you this page again. Why is it not level? Okay, just to make sure, right, that should be good enough.